Okay, so I don't know how much we'll get done today, but for the next 2 lectures, we want to talk about resolutions. And derive functors. So let's say this is part 1. And today I'll focus more on projective resolutions. Maybe I'll have time to talk about injective at the end. So, so recall from last time, a module, let's say P over some ring is called projective if, for all surjections, let me say it like this. If in all diagrams of the following form, so I have a map from one module to another which is surjective. I'll write Q for a quotient, and a map here from P. There's a lift of F tilde. So if in all diagrams of this form, the lift F tilde of F exists. And injective was a kind of dual notion, where there was an extension for every injection. And we saw that a module was projective precisely when it was a summand of a free module. And so note, given a module, given any module, not necessarily projective, there's a surjection from a free module. In particular, a projective module. So I'll call this epsilon. Okay, this is from a projective module. So for instance, I could choose a set of generators of X that would give a surjection from a free module, and a free module is in particular projective. So a surjection from a projective module. Then I can choose a surjection onto the kernel of this map epsilon. Okay, so this kernel is a submodule of P naught. So this is also from a projective module. And so on. And so if I continue in this way, I look at the kernel of this map from P1 to the kernel of epsilon. That will have a kernel. I can surject onto it by P2 and so on. And if I keep doing this, I get what's called a projective resolution. Okay. So, and so on. So let me give the formal definition. For which I just gave instructions how to construct an example. So given a module X at projective resolution of X is a complex with projective terms. So let's say an R complex, so it's a complex of R modules, for which the differentials are R linear, is an R complex. I'll write it as P dot. Consisting of, so with projective terms, each Pi is projective. With projective terms, and from P0 to X, there should be a map of this form epsilon. So this should be a surjection such that, so this complex P dot should only have homology in degree 0. Its homology in degree 0 should be X. So a concise way to say that is that the kind of induced map from P dot to X, where X is thought of as a complex in degree 0, this should be a quasi-isomorphism. That's saying there's homology only in degree 0. Okay, so no higher homology. So that's what projective resolution is, and this construction shows that every module has a projective resolution. And so they exist. They're not exactly unique, but they're unique up to homotopy. So this is very important. So let me formulate the lemma. So lemma, sort of, say it like this, lifting module maps to maps of complexes. So lifting module maps to chain maps. It's the lemma that tells you how to do this and how well it works. So I'll prove it in a little greater generality than we need, just the generality that worked for the proof. So the situation is the following. So suppose I have a map of modules, X to Y, in our modules. And we're given a complex of projectives, not necessarily exact even, that's not important. P dot together with a map epsilon x to x, and a resolution, not even projective, just a big, long, exact sequence going off to the left. So this one is a resolution. It should be a quasi-isomorphism. So this is not necessarily projective. It doesn't matter. All that matters is that its homology in degree 0 is y. And there's no higher homology. Then there's a lift of f to a chain map between these. So let me spell that out. So I have a complex that looks like this. And another complex that looks like this, Q0, Q1, and so on. I'm given this map F, so this is all the data that's given. And the lemma asserts that I can fill this in. So I can find a map F0 making this square commute, a map F1 making this square commute, and so on. So these, let's see. P, Q, and so on. And such a lift, any two such lifts are homotopic. So the lift is maybe not unique, but if I made two different choices, they'll be homotopic. So we'll construct a homotopy between them. In particular, this means any two projective resolutions of a module are homotopy equivalent. So this follows from just lifting the identity map on the module. Okay, I'll give a little more detail of the last statement in the proof, just to be clear. Okay, so proof. We need to construct this lift using the properties we have. All we really know is that these terms are projective, so they satisfy some kind of lifting property. And this sequence down here is exact. Okay, so we'll do it inductively. So let's see. So this one, these maps are surjective. This one is not even so important that it be surjective. But this one's a resolution of y, so the last term is surjective. So since P0 is projective, and epsilon y is surjective, This composite is just a map to y, and it lifts along this surjection. Okay. So F0, a lift, there exists a lift F0 of this composite, epsilon x followed by f. Okay? And what? I want to continue. So let's look at what the image of this F0 is. Just a sec. No, that's fine. Let's look at this composite, P1 to P0 to Q0. Okay? If I do P1 to P0 to Q0 and then keep going, that would be the same as going P1 to P0 to x and then down to y, because this square now commutes. But this composite's 0. Okay? Therefore, this composite lies in the kernel of epsilon y. So next, since, let me write out that composite, D1P F0 epsilon y equals D1P epsilon x f, the composite which is D1P F0 has image in the kernel of epsilon y. So this, because this is 0. So has image in kernel of epsilon y, but this bottom sequence is exact. So the kernel of epsilon y is the image of D1Q. Okay, and so now we're in a situation where we can use projectivity of P1 again. So now, since P1 is projective, the composite P1 to P0, let me write it like this. So it's P1 to image D1Q lifts along a surjection from Q1. Okay, and so that gives F1. And continuing in the same way, you'll find that P2 to P1 to Q1 lands in the image of D1Q2, D2Q. So, so you continue by induction. To construct the rest of the lifts all the way out. So that gives the existence of a lifting. And now we want to compare two liftings. Okay. Y is what? Here. Right, so what should I assume? I assumed that this was a complex and a map of complexes. So it's built into the hypothesis. What is a map of complexes of this form? It's a map like that. Okay. Okay. So that gives the existence of a lift of the map of modules to a map of these complexes. And now, to compare two lifts, let's suppose we have two lifts. two lifts of the following form. Let's say f dot and f dot prime. Okay. We claim that they're homotopic, so we want their difference to be null homotopic. And we'll construct this null homotopy inductively, just like we constructed the lift inductively. So let's see what we can do. Okay, so let's begin. So I have x to y. That's my map F. I have P0 and Q0, like this. I have P1, Q1, and here I'm looking at the difference of the two F0s, F0 and F0 prime. F0 minus F0 prime. And here I have F1 minus F1 prime, and so on. Okay, very good. And I want to find the null homotopy, so I need maps back like this. So this will, let's call it S minus 1, S0, S1. And remember what the null homotopy will say. It says this followed by this plus this followed by that will equal the difference, right? But let's look at the difference here to begin with. So what can we say about the difference? Consider the composite. Let's see. This is my epsilon y. So let's consider epsilon y applied to the difference. Then that's the same as, because each of them individually commute over here, this is the same as d1, epsilon x, this is epsilon x, followed by f, minus f epsilon x. So the whole thing is 0. And so whatever the difference is, it lands, again, in the image of this differential, which is the kernel of this. So that means this difference is a map from P0 to the kernel of epsilon y, which is the image of d1q. And that's surjected onto by q1. Okay? So let S0, I'll let S minus 1 be 0, and I'll let S0 lift this difference to Q1. Okay? So because it's a lift, that means that I'll have what? I'll have S0 followed by D1Q equals this difference. And there's really another term of the form epsilon x, s minus 1, but I didn't write it because it's 0. Okay, so now we got to continue like this. So now we have our S0. And so we want this D1P followed by S0, plus we want to find this S1. S1 D2Q, we want the sum of those to equal the difference of the two Fs. But we don't yet know what S1 is. We're going to have to solve for it. So now we want to find S1 such that what? such that S1 d d2q plus d1p S0 equals this difference. F1 minus F1 prime. And so it's a little more convenient to write it as we're going to solve for this S1 where it's this term minus this term. And then that will be a lifting condition. So consider F1 minus F1 prime minus this term which is given, S0 d1p. Okay. Is that what I wanted? Did I write that correctly? Yes, I did write that correctly. Okay, so consider this term. And now, where does it land? It lands in Q1. Apply the differential. Okay, so apply d1q. What do we get? We get d1q f1 minus d1q f1 prime minus d1q S0 d1p. Yes? And what is that? Well, let these be what they are. What is this? We constructed S0 so that S0 d1q was the difference of the F0s. Okay? So this is equal to d1q f1 minus d1q f1 prime minus what? Minus F0 minus F0 prime. Okay? And because each of F0 and F1 made this square commute with d1p here and d1q there, this term and this term will vanish. They'll cancel each other because they have opposite signs. And similarly here for F0 prime and F1 prime. So that's because the original collection of FIs and FI primes each form chain maps. Okay. And so what does that mean? It means that this difference F1 minus F1 prime minus S0 followed by D1Q, that lands inside the kernel. Sorry, D1P followed by S naught. That lands in the kernel of D1Q. So what do we get? We get that F1 minus F1 prime minus S0 D1P. What is it? It's a map from P1 to kernel of D1Q, which is image of D2Q. And now this is surjected onto by Q2, so I can lift. Okay. So let S1 from P2, sorry, am I doing P1 or P2? Just a minute. P1, yes. P1 to Q2 be the lift of this along this surjection from Q2 to the image of its differential. Okay? And then proceed inductively. Okay? To construct S2 by lifting the appropriate difference, and S3 by lifting the appropriate difference, and so on. Okay? So are there any questions about this inductive construction? How it worked? No? Okay. So I'll just make a last comment about this last comment. They didn't need two projective resolutions of a modular homotopy equivalent. I'll just spell that out because it's important. So finally, suppose P dot and P dot prime are two projective resolutions of X. Then, if I lift the identity on X, we'll get chain maps from one to the other. Let's call it F, but also the other way around. It doesn't matter which one's which. Okay, so let's call that G. And now the composite, in either order, also lifts the identity. So the composites, call it maybe dot, F dot followed by G dot, and G dot followed by F dot. These also lift the identity. But now they're from P to P and from P prime to P prime. And so if I just wanted to lift the identity from P to P, I could just take the identity lift. Okay. But the identity lifts. So by uniqueness, so homotopy uniqueness, these two composites are homotopic to the things that are the identity in every degree. So this is, let me write it like this. So which one was this? G goes from P prime, so this would be the identity map from the P prime complex to itself. And in the opposite order, the identity map from the P complex to itself. Okay? So the projective resolutions are not unique, but they're unique up the homotopy. And that's good enough in practice. Very good. Okay, so that's the important lemma about constructing maps between resolutions. And we need one more thing in order to get the whole machine off the ground. we need to know how these projective resolutions are compatible with short exec sequences. Okay. So there's one more lemma that we need. This is called the Horseshoe Lemma. At least in English. I should have looked up what it's called in Russian. The Russian names for these things are often different and often amusing. So there's a theorem in topology about, on a vector field on a sphere, should always have a 0 somewhere. So somewhere on the surface of the Earth, the wind is not blowing. And in Russian, this is called the theorem of the hedgehog. Because when the hedgehog rolls up like this, one spine should be sticking straight up somewhere. So the Horseshoe Lemma says the following. So suppose Suppose 0, how do I want to do this? Yeah, I'll do it like this. 0 to x to y to z to 0 is a short exec sequence of modules. All right, SES, let's say, of R modules. And suppose I have projective resolutions of x and of z, but not yet of the one in the middle, y. So we are given projective resolutions let's say P dot and Q dot of the two outer terms, x and z. Then I don't have a good name for the complex in the middle. So then there is a projective resolution let me just call it R dot, maybe. That's unfortunate because I called R the other thing. So here's a better notation. Sorry about this. So let me call this a short exec sequence like this, and let me call this one P prime, and this one P double prime. Then I'll put the projective resolution P in the middle. So there's a projective resolution P such that its terms, so Pi is going to be Pi prime plus Pi double prime. So the terms are just the sum of the terms from the two resolutions in the outer bit, but the differential is not quite a sum, it's upper triangular. So differential will be of the following form. So a differential of the form will look as follows. So let's suppose it's in degree I. What does it look like? On this summand, it will just be the differential from that complex. And over here, it will be the differential for the other complex. But there'll be an additional term right here. We have to give it some name. I'm not sure what to call it. Maybe I'll call it phi. Okay, so phi e, where phi e is what? So it's going from this, and it drops the degree by 1. And so this phi e will be from pi double prime to pi minus 1 with a single prime. So it's just the other summand, right? Okay. And then once you have that, it's clear that pi prime will form a subcomplex here, and that the quotient complex will be p1 prime. And so then we get a short exact sequence of complexes, let's say of resolutions, which will look as follows. So I have x prime, x double prime. That was my original short exact sequence. I have a resolution like that. So I started out with a short exact sequence. I chose two projective resolutions in the outer term. I kind of pieced them together to get a resolution in the middle term, and that will all fit together into a short exact sequence of complexes. Okay, and this lifts this, and this lifts that. So this is the statement of the lemma. And the proof will be kind of similar to this proof about lifting maps. It will proceed inductively, using lifter properties for projective modules. Are there any statements about, any questions about the statement of the lemma? It's just a map of our modules. That's all. It's just some map of our modules. So I'm just telling you there's going to be a differential, but I'm telling you more than I'm telling you the shape of the differential. I'm telling you in the course of the proof we'll construct the phi i's so that the differential will have this form. When I evaluate it on something which lives in this summand, it will just be the differential on p prime. When I evaluate it on an element from this summand, it will be phi I plus the differential on p double prime.
Does it have anything to do with space horseshoe?
Sorry?
Does it have anything to do with space horseshoe and dynamics?
No. I think the reason it's called the horseshoe lemma is because of this shape right here. This is the horseshoe right here. And as we proceed in the proof, you'll see this kind of horseshoe that needs to be filled in at step by step. So no, there's no dynamics here. We talked about in the seminar last time how you try to combine topology with homological algebra, but that's something very subtle. Okay. So proof. So it's going to be an inductive construction. Let's start on with what happens in P0. So we'll construct inductively. And how does this go? So let's start with one of the horseshoes. So we're starting with surjections like this. This is a surjection. And this can be lifted. Right? This is a surjection, this is projective, so this map lifts. Okay? So this will be the phi 0. Okay? And then here I'll put p0 prime plus p0 double prime. This will just be the obvious inclusion and quotient. And I have to tell you what this map is. So this was, I don't know, epsilon prime. This is epsilon double prime. So this map here will just be the sum of epsilon prime plus phi 0. And because phi 0 lifts epsilon double prime, when I compose down here, this will commute. Okay? So, so phi 0, choose phi 0 to lift epsilon double prime along the surjection from x to x prime, and define epsilon, so this map, to be epsilon prime plus phi 0. So it does indeed have this form. Did this make sense? Just a sec. Yes. It will have this. So this is for I. This is I greater than or equal to 1. There's no term like this at the beginning in kind of degree minus 1. Okay, so now, once at this step, now we have the following situation. So now take kernel of these maps from left to right and apply the snake lemma. So this is a short exact sequence. This is a short exact sequence. We have a map of them. So the kernels will fit into some long exact sequence. Of kernels of the source to co-kernels of the target. But all of these maps are surjective. So the co-kernels of the target will be 0. So we'll get the following. So what do we get? We get p0 prime, p0 prime plus p0 double prime, p0 double prime. Here we have epsilon, epsilon double prime, epsilon prime, and the kernels. And all of these in the vertical direction. That's kernel of epsilon prime, kernel of epsilon, kernel of epsilon double prime. And the snake lemma says that there's an exact sequence like this. And normally, it would say that there's a connecting map to the co-kernel over here. But the co-kernel is 0. So in fact, this is already short exact. So over here, co-kernel epsilon equals 0. And so on. Okay? And so now we're in this situation where I've replaced x prime x and x double prime with these kernels. And these are surjected onto by p1 prime and p1 double prime. And so now I have a new horseshoe. And I can continue. So now continue, so repeat on the new horseshoe. So this map here is a surjection, and I can lift this to phi 1.
Why the maps from P1 prime to kernel of epsilon prime and respectively to double primes are surjections?
Because we assumed from the beginning, I've rubbed off the statement, that the map from p prime dot to x prime was a resolution. So that means when I write down the whole sequence together with the x prime term, the whole thing is exact. So kernel of this equals image of this. So we repeat on the new horseshoe. We choose phi 1 to lift along the surjection of kernels. Okay. And just continue in this way. We use the snake lemma to know that when we pass to kernels of this map of short exact sequences, I got some short exact sequence like this. I use the additional fact that the next term actually should be a co-kernel up here, but that happens to be 0. Otherwise, it just would have been exact on one side, and then there would be an additional term. But in this case, that doesn't happen.
So you don't need p prime to be projected, right?
Pardon?
You don't need p prime to be projected.
That is true. I think I never used that it's projective. I did, in order to apply the snake lemma. Right? Because the target sequence in the snake lemma should be exact on the left. But indeed, I don't think I needed to know that the p prime terms were projective. Okay. That's a good point. I do want the middle to be, I mean, what we're trying to do is put together two projective resolutions to get something projective. So the construction seems to work. It just doesn't produce what we want. Okay. And this second statement about the shape of the differential is now, it's kind of clear by construction. Right, so now, so we choose this and we define yeah, no, that's fine. And we define the map now to this kernel to be the sum of, so on this term, it's just d1 p prime, and on the other term, it's phi 1. Okay. And then if you compose all the way to here and project, you'll see that the other term has this in it. Okay. Very good. Okay, so that's the horseshoe lemma. And why is this important? So this is going to be important in proving properties of derived functors. So I need to tell you what derived functors are and what properties they have. Okay, I can still go there. I'll leave this for now. Okay, so that's about projective resolutions and their basic properties. Now for derived functors. So left derived functors. We'll talk about right derived functors probably next time. So you can do this in some greater generality for certain kinds of abelian categories. And I decided to start out by doing this for modules, just because it's more concrete. So you remember we had this problem last time. The reason we introduced projective and injective things is that we had certain functors, say like tensor, which preserve surjections but not injections. And they took short exact sequences in general to right exact sequences. So that happens a lot, especially for tensor product, but for other things. And we would like to measure the degree to which some functor is failing to be exact on the left. And this failure is, you could say, measured by these left-derived functors. Alternatively, you could say that there was something wrong with your functor to begin with, and you should fix it before you apply it. And then this is kind of the true kind of homologically meaningful version of your functor. Okay, so given a right exact functor, so it takes short exact sequences to right exact sequences, but maybe breaks exactness on the left. So let's suppose, for example, f is from R mod to S mod. So for example, such a functor might be of the form tensor with a bimodule, like that. Then we can take a projective resolution of every module before applying the functor. Let's choose a projective resolution. So maybe I'll call this M because I want to use X for my kind of variable module. So let's choose a projective resolution P dot to X of every module X. In the end, whatever we're going to do with this will turn out not to depend on the resolution because of this homotopy uniqueness that we proved. So of every module. And let's define new modules. Let's apply F. To the resolution, term by term. Okay, so the composite of two terms in the resolution, it's a complex, there's 0. And the functor, being right exact, preserves that the composite of two things is 0. And so we get a new complex. It will be f of p0, f of p1, and so on. Okay? And because f is right exact, the zeroth homology of this complex will just be f of x. But it may have higher homology. Okay, so since f is right exact, H0 of f of p dot will just be f of x. But there can be higher homology. If f is not left exact. Okay, so definition, what is this higher homology has a name. Okay, so the ith maybe it's kind of a definition lemma. So part of the definition is that it's well defined and it works. So the functor LIF computed as HI of f applied to any projective resolution. So this is any projective resolution. This is called the ith left or right functor of f. And we'll give examples in a moment. So let's first check that this is really well defined and that it is a functor. So note, because any two projective resolutions are homotopic, and homotopy equivalences induce isomorphisms in homology. Okay. This is actually well defined. So note, since any two projective resolutions are homotopic, LIF of x up to isomorphism is independent of projective resolution up to isomorphism. And in fact, this isomorphism itself is unique. So just because no matter two ways you compute something, you always get something isomorphic, maybe that's not very natural. Maybe you have to choose the isomorphism between them in some random way. But this is not the case because if I have two resolutions p to p prime, and I choose the homotopy equivalence between those, and then I choose a homotopy equivalence from p prime to p back, I know that the composite is homotopic to the identity. And therefore induces the identity map on homology. So since any two projective resolutions are homotopic, okay. So this is resolution up to unique isomorphism. And moreover, by this lifting, if I have a map from modules x to y, I can lift that to a map of resolutions. And any two such lifts are homotopic, so they induce the same map in homology. So that means by lifting of maps to chain maps, of module maps to chain maps the LIF are functorial. Okay, so very good. So I want to give some examples. And then we'll have to study the formal properties of these derived functors in more detail. So let me give an example. This is probably the most important example. So suppose, maybe it's definition. It's an, I'll give a definition of an example of this. So suppose let maybe M be a, let's see, S R bimodule, then we have a left exact functor given by tensoring. Sorry, right exact. And so it has left-derived functors that you compute via projective resolutions. In fact, you could always choose a free resolution that will in particular be projective. And the left-derived functors have their own name. So then the left-derived functors left-derived functors are denoted tor I. It's a bimodule, so you should kind of indicate how S is acting. And yes, M blank. I could have done it on the other side as well. So if we'll do this later. I maybe fill in this variable and leave this one blank. So these are so-called tor functors, and let's do an example. Okay, so I want to compute tor I between some finite abelian groups. Let's do finite cyclic abelian groups. So, so let's compute tor I. I'll just consider these as just abelian groups, so Z acts on both sides. Z mod n. And Z mod n. Okay, and the recipe was to resolve the variable module. Okay, so the recipe is the following. I choose a projective resolution. Let's choose the obvious one. Let's choose, in fact, the free resolution. Which is Z surjects onto here in the usual way. The kernel is surjected onto by multiplication by Z. The kernel is n times Z. So there's my free resolution. And then it has two terms. This is degree 0, degree 1. And then I have to tensor that with Z mod M. Okay. So then towards 0, well, we already know that that's supposed to be the functor just applied to Z mod N, but we can see it, right? So what is it? It's supposed to be kernel of this, which will be everything, modulo the image. So this will be co-kernel of, if I tensor Z with Z mod M, I'll get Z mod M. And the differential will be multiplication by n. Right, so this will be Z modulo the ideal journey by m and n. And what is the ideal journey by m and n? It's the GCD of m and n, right? The greatest common divisor. And what is Tor 1? Tor 1 in this case, it's, well, I tensor these two terms and I take kernel modulo image. The image is 0, so I just have kernel. So this is kernel of this map. And that's the so-called n torsion. Okay, so that's where the terminology tor comes from. So this is x in Z mod M such that n times x is 0 in Z mod M. Okay, so there it is. That's our first calculation of derived functors. There are no higher ones because our resolution only had length 1. In general, for more complicated rings or complicated modules over complicated rings, the resolutions can be infinitely long. So let's see. We could probably do an example. I want to give a property. We'll do more examples in the seminar. Okay, right, so basic properties. So let me state this as a proposition. Right, so the proposition is given a right exact functor f from R mod to S mod the left-derived functor, the ith left-derived functor, sorry, let me say it like this. Okay, so given a right exact functor and a short exact sequence of modules of R modules. I can apply f to it and get a right exact sequence. And what the left-derived functors do is complete this to a long exact sequence. So there is a natural, there's a natural long exact sequence. That goes as follows. So this, so far, notice we haven't used the horseshoe lemma. This is where we use the horseshoe lemma. We've just used this lemma about lifting maps of modules to chain maps. And the horseshoe lemma was about resolving not just individual modules, but kind of resolving modules in a way compatible with short exact sequences. So there is a natural long exact sequence that looks as follows. So we'll have f of z, that's L0. F of y, f of x. And then there's a term, L1 f of z. And there's a connecting map. I guess I'll call it delta 1. And then L1 f of y, L1 f of x, and then there'll be a connecting map, delta 2. This will be L2 f of z, and so on. Okay. And natural here, I said natural. Natural means natural in the maps of short exact sequences. So natural means given a map of short exact sequences. So suppose I have one of them, and I have another one, and I have maps like this, F, G, and H, making everything commute, then I get a long exact sequence with derived functors here and here, and I will get a commutative diagram of long exact sequences. And in fact, you can say even more. These left-derived functors are kind of the universal way to do this, to take short exact sequences to long exact sequences, to take maps of short exact sequences to maps of long exact sequences, such that in degree 0 you had the f you started with. But we don't really need this. Okay? So I will give a proof of the first part. The naturality is kind of elementary, but takes a long time. So I'll probably make that into an exercise, because we only have a few minutes. So let me just quickly say what to do. This is where we use the horseshoe lemma. So proof. So use the horseshoe lemma to replace this short exact sequence with a short exact sequence of projective resolutions. So it'll be let's call it P dot X, P dot Y, P dot Z. And since I'll construct this using the horseshoe lemma, in each degree, this will be a sum of the two outer terms. So the differential is not a sum, but the term by term, it's a sum. And then applying F, I claim we again get a short exact sequence of complexes. We get a short exact sequence of complexes. Zero f of the resolution of x, f of the resolution of y, f of resolution of z. And because in each degree, this is a sum, and f commutes with direct sums, because it's right exact. This sequence will be split in each degree, and therefore it will be a short exact sequence of complexes. So it's indeed short exact because in every degree, we'll have something like this. I'll have f of the sum and f preserves direct sums. Okay. And now take the long exact sequence for this short exact sequence of complexes, and it will give you this long exact sequence. So then the long exact sequence of homology for star gives the desired long exact sequence. And you have to do a little more work for naturality. It's not really hard, but it does, it's some long inductive construction. So you need to check naturality, and I'll make this into an exercise. It's good practice with the kinds of lifting arguments that we were given before. Okay, so we'll stop there. Any more questions?